Okay. So first things first, I graded the test and handed it back, and everyone did amazingly well, which shows that with hard work, everyone can succeed. And here's the key. You got to keep it up now for a couple more tests and like, what, 6 more weeks in the semester? And I think that's doable if you keep working hard. I was pleasantly surprised.
Notes for that last chapter. I feel like that made a huge difference for me.
Well, we'll try to have really good notes for this chapter then. So we're going to look at chapter 10. And what chapter 10 is an introduction to quantum mechanics. And you guys probably get more than you should from this, or more of the quantum mechanics than you really should, but that's okay. You guys are all capable of learning it. And really what we're not going to focus so much on is really like the messy, nasty equations or anything like that. There's not a single equation in this chapter that I can think of. What we're going to focus on is using the ideas behind it. So there's kind of a couple goals that we want to talk about and see. So the first off is, like chapter 5, there's a lot of history. And so the questions in the history section will be similar to the questions in chapter 5. And what we primarily want to focus on is sort of the evolution of the model of our atom. And what we're really going to do is we're going to have some back history. And then basically we're going to hit Rutherford, and you guys remember him? And then we'll go forward. This is just an outline. I don't know if you need to put this in your notes or not. It's kind of up to you guys. So again, I don't want you to memorize dates, but what I do want you to memorize, or I shouldn't even use the word memorize, what I do want you to learn and kind of focus on is sort of what's good about each model and why we went to that model, and then what caused us to change that model. I want you to focus on the process that it's occurring. The second thing that we're going to kind of look at is we really will look at quantum numbers and where an electron is around an atom. And again, what we'll do is we'll go deep, meaning we'll talk about it deeper than what we really need to use it, and then basically we kind of lighten up in chapter 11. So we make use of all the stuff we learned, but we also realize that we don't need to know the nitty-gritties behind all the details if we can memorize a few simple rules to use as sort of rules of thumb for things like that. And then kind of the other thing that we want to focus on or look at is how, and this is going into chapter 11 somewhat, but how the quantum mechanics can explain the periodic table. And it's also going to explain other things that we were told, plus other things. So for instance, we know that sodium forms a +1 ion. Why? Simply because J said so, right? Hopefully what we're going to have at the end of this is not a J said so, but I understand why sodium forms a +1 cation. We'll look at why things form ions, and then the final transition, and this is going into chapter 11, is we're going to learn about molecular compounds.
Other things.
Yes. Plus other things, meaning we'll understand, explain the shape of the periodic table, and then we'll also be able to explain other things that we've already learned at a deeper level. So we're always going to go back and say, hey, remember when we talked about this? This is how quantum mechanics explains it, or this is how this theory can explain that, and allow us to move forward. And then, of course, chapter 11, which is our end goal for all of this information, is we'll look at how molecular compounds are formed, molecular compounds, and how we share electrons. Because one of the things I said at the beginning of the semester is we learn about ionic compounds way before we ever learn about molecular compounds. We'll learn why CO exists, CO2 exists, but there's no such thing as CO3. We'll learn to predict things like that and to be able to decide what's likely to exist and what's likely to not. Now, there are... Yes?
I have an extra jacket.
Can you go back?
Like freezing.
You can close the door if you really want, and or all my jackets are out in my truck.
Never borrow yours. It's just sitting there.
Yeah.
Can I borrow yours?
You don't think, do you?
No, it's not. Cheap. But
Okay. Let it be noted that Jay is a gentleman, and we're not talking about the Jay talking, we're talking about the Jay sitting and listening with the awesome hat.
Thank
Oh, and that's how all the cool kids do it. So you've got a bunch of tools also available for you on the internet, and I've already handed out one of them. This pictorial study guide to chapter 10 and 11, to me, is probably the single most useful tool for studying in this chapter. It really does contain just about everything that I could squeeze on it and then some. The only thing I would argue is that there's too much on some of the pages, that we could spread it out over a bunch of pages. But it is a very good summary of everything we're looking at. So let's start a little bit with that back history, meaning we're going to fill in some gaps. So we recall that we had that debate about atoms, whether they were sort of continuous or whether they were discrete. And that was our Empedocles versus Democritus, right? I don't even care if they're spelled right. Empedocles and Democritus. And are either continuous or discrete, meaning that atoms can either be, there's a smallest indivisible part, or what Empedocles and those guys said is things like air, earth, wind, and fire, and that you could have any amount of an atom, that there wasn't like a fundamental unit like a single atom. Well, there's a similar debate over the nature of light. And the question is, what is light? And there were two major schools of thought. There was one that was led by Sir Isaac Newton. Have you guys heard of him?
No.
Okay, let it be known for the record, that is Jay trying to be funny and failing. And then the other guy is Christian Huygens. Now, have you guys heard of him? Yeah, maybe there's a reason for that, maybe not. So we know Sir Isaac Newton pretty well. What he believed in is a particle nature of light. And they called it corpuscular. Corpuscular. And Sir Christian Huygens said that light is really a wave. So this is way back. I guess maybe we should put a date. We're going to say approximately the 1600s. Again, date's not so important other than to kind of fix it in our mind about where we are. So this is well before our Rutherford models, right? And even Dalton. Jess, what's your question?
How do you spell his last name?
Huygens. At least that's how it's spelled in my handout. I wouldn't know how to spell it to save my life. Plus there's like 2 A's in Christian. Either that or I typoed it. I don't know. I'm not so worried about the spelling of the names as long as you get close. And so both of these people are very brilliant men. Unfortunately, Sir Isaac Newton is sometimes considered the greatest and most influential scientist ever. That's a pretty big title, right? Whereas poor Christian Huygens, I mean, he did do some cool things. For instance, he invented pendulum clocks, which I think is kind of neat. Yeah. It's constantly turning between kinetic and potential. And he also was very good at and wrote one of the first books on probability theory. So it's not like he was, not very smart or anything. Oops, theory book. But I got to be honest, Sir Isaac Newton is the man, right? And so for about 200 plus years, for about 200 plus years, this ongoing theory between particles and waves for the nature of light is going back and forth, back and forth, back and forth, with the majority of people supporting the Sir Isaac Newton model, that light really is little particles that bounce around. Now, when I say light, what do you guys normally think of? Waves, right? And so one of the things we're going to see is that obviously we need to change, or that this evolved into sort of the wave nature of light. But way back then, Sir Isaac Newton says it's particles.
I can't take you seriously today, Jay. I just can't do it. Try really hard.
Okay, so for 200 plus years, particles are winning. And there's a lot of, things that say particles are light and light can be particles or light can be waves. And you can actually explain a lot of phenomenon both ways very easily. And sometimes one way is slightly better to think about, and sometimes the other way is slightly better to think about, but certainly there's no clear winner.
Is that 200 years or
200 years. So the next person, or the next two people, sort of cement the idea that really light is a wave. And if you think about it, these people had to overcome some serious inertia, because they're saying, no, Sir Isaac Newton was wrong. And that's like saying basically God is wrong to a lot of people. You know, you just don't hear that too often, do you? Actually, around here, well, so, what? I don't know. They're doing a lot of work over there. So he performs an experiment called the double slit experiment. And what he does is he has two slits right here. Double slit experiment. And if we have light as a particle, meaning if light is a particle, then what you really should see is two beams of light, right? But if light is a wave, instead what you should see through these two slits, so if light's a wave, if we kind of think about it like this, and again, the picture in the handout's 10 times better than the picture I'm going to draw, we should see that from each of those holes, we get another series of waves forming. And you can actually do this experiment in what's called a wave tank, where you basically have just a giant aquarium, and you can generate the waves, and you can put it through slits or like around a pier on a dock or something like that. And what you get is a series of bright and dark lines. Okay. Okay. So I draw too fast. So there's the bright and dark lines, and you know, I guess I could try to draw the pattern, but I'll be honest, look on the handout. And if you want to see a color version of the handout, go ahead and look and open it up on the web, since I know some of the things don't come through very well in the black and white version of it, but you know, that's what we print out in class. And so what this bright and dark lines are due to is something called constructive interference and destructive interference. And this is something that cannot be explained by particles. And so here we have clearly sort of that light is a wave, and that the wave phenomenon is the best way to describe it. Now, of course, people are going to say, well, no, we'll figure out a way to explain this with particles. But it turns out that you really can't explain this with particles. The other experiment that they kind of did was to use something called polarized light. And we'll talk about polarized light second semester. It's one of the fundamental differences between an important class kind of molecules that we're talking about. And the idea is that polarized light vibrates in one direction. So the second experiment, you want me to just go back?
Yeah, just for a second. Okay.
Now you guys are familiar with maybe not polarized light, but you guys have seen or heard about polarized filters, right? So for instance, like sunglasses that are polarized, so you can see only certain reflections of light and it blocks out others. Same thing, if I have a light wave like this, and I have a filter that is perpendicular to it, no light passes. Whereas if light is a particle, and I have a perpendicular filter, it really means nothing. And light passes right through. So, because this is what really happens in real life, that's sort of that second piece of information that proves that light is a wave. So, now everyone thinks light's a wave, right? Wonderful.
Why does it go through?
Okay, so if it's a particle, it doesn't. Okay, so think about it kind of. Okay, imagine a fence, right? So here's my fence. Here's my rail. What?
What does that say more that means?
Means nothing? I don't know. Oh, light. Yeah, meaning the filter doesn't stop anything. So think about it like a fence. You can throw baseballs through a fence, right?
No. Hang on.
Well,
That fence, yes, you could.
like a big wide fence, right? Heck, you can probably squeeze yourself through if you try. Now, if light's a wave, maybe we can think about it as if the wave is parallel, goes up and down with the fence, then it goes right through. But if the wave goes this way and hits the fence, then it can't go right through. So depending upon which way light is vibrating, whether the wave is going up and down or the wave is perpendicular, means that light can either pass through the fence or light can't pass through the fence. And so that's the behavior we see when we really do use filters to try to block certain wavelengths of light. Now, one of the things I'm going to tell you is don't worry about these experiments in too much detail, other than kind of being able to say the two experiments were, double slit experiment and polarized light, perhaps. Meaning, I'm not going into enough detail about these experiments for you to want to understand them. What I'm trying to do is set up the whole idea that there's this huge debate going on. And because of this debate, certain views that's going to affect how we treat the Rutherford model of the atom. So this is all like backstory before we get to kind of what we really want. The other piece of person that we want to mention at least is James Clerk Maxwell. And basically what he came up with is 4 equations to describe electricity, magnetism, and optics, or basically we can think about it as light, in terms of waves. And these 4 equations were monumental and basically led everyone to say, well, okay, we've got a great mathematical model for this. It predicts everything very nicely. We can find no flaws with it. And so, we're really beginning to think about that.
What's the over?
Optics? You guys have to stop. A good note-taking skill is to not write down what I write on the board, but listen and write what you think you need to write down to remember.
Is that after electricity?
Magnetism. I don't know if I should even talk. Maybe I should just write and you guys should just read.
I told you I look at your lecture
Oh,
notes.
I know. I believe it, actually. So the other piece, he's considered the 3rd greatest scientist of all time. Who do you think is second? Yeah. So we'll talk about Einstein later. So, these are some pretty important people. And, it turns out that even though Sir Isaac Newton is considered one of the greatest scientists to ever live, he was wrong about this. Kind of. And we'll see that kind of is the part that makes quantum mechanics confusing. But we'll get there shortly. So, let's take a look at the Rutherford model of the atom.
Is this one of James' experiments?
No.
Equations or whatever?
Nope, this is just
Whole new thing?
right. So the idea is that he came up with 4 equations to describe things. Everyone believes these equations. So everyone really believes that light fundamentally is a wave at this point, kind of like what we normally think about it these days, and that these equations could really describe all of the observed phenomena. Now we're going to see that that's not quite true, but at the time it is. So what do you guys remember about the Rutherford model?
Protons in the middle and electrons.
Yeah, protons in the nucleus, and then we can think about it as a cloud of electrons. And so we've got positive charge in the nucleus. We have the negative charge in a very large cloud. So what happens next is that there's an actual experiment made to kind of test parts of the way the Rutherford model works. And so the experiment is called line spectra, or we can refer to it as that. And if we think of light normally as a wave, and we put it through a prism, what happens?
It bounces off or refracts.
Yeah, and what do we get?
Color.
Yeah, we get the rainbow, right? And so the idea is, up here might be blue, and down here is red, and somewhere in between is green, isn't it? I don't know. I don't remember Roy G. Biv very well, except for that.
Red, orange, yellow, green, that's all you
Yeah. Meaning, I don't care if I have the colors in the right order. How about that? The idea is that it predicts this rainbow of clouds. Now what happens, though, a rainbow of clouds, it predicts a rainbow of colors.
Wait, is this the thing that looks like a crystal and then you put it in light, it's the rainbow? Is that what
Yeah.
Is somebody specific to this experiment?
Yes, but we don't care what his name is. I actually can well, see, that's where it's tough. The person that first did the experiment could never explain it. So, yeah, he gets credit for the experiment, but he doesn't get any credit for explaining it. The person that explained it first came up with an explanation, and this is going way too deep, so don't worry about it. Came up with an explanation, but could not explain why his explanation worked, really. Meaning he said, here's a mathematical model that describes it, I have no idea why it works. The person that finally explained it, is Bohr. Now, the question is then, who do we want to give credit to? The person that first did it, the person that kind of explained it, or the person that really explained it? And honestly, I don't even really care which scientist is associated with this. This is simply line spectra, or that concept. So what happens now if I take light and I shine it at an atom is that I don't get a rainbow. Do not get a rainbow, as predicted by Rutherford. So the way Rutherford's model would work is if I've got an electron and I've got things like this, if I shone light at it, then I could get all colors out. What really happens is we only get a few colors out. And that's why they're called line spectra. So instead of getting an entire rainbow, you might just get one small little portion of blue light, and you might get one little small portion of green light.
you're saying that it runs towards more than one right, and then
It would predict every color possible. And because when they did the experiment, they only got very specific colors out that were different for different elements. That obviously something more was happening. That the electrons couldn't possibly just be in some random cloud around the nucleus. That there had to be some structure that led to only certain colors of light being emitted by those atoms. And so this phenomenon is what's actually responsible, for instance, where, like, when we watch fireworks, they have different colored fireworks, right? Well, depending upon what color of firework you're seeing, that's produced by a different element for each different type of color in the fireworks. For instance, the pretty red fireworks you see, I think, are rubidium. and the really deep blue ones are cesium. And so each element has a very particular color that's, you know, sort of the most common. Like sodium is a bright yellow. And so somehow they have to explain why each element is a different color and why it doesn't just emit any color of light when it's excited or when you pass a beam of light through it. And so this is the problem. This is the first big problem with Rutherford. And it took quite a long time to kind of explain it. And there's two people that had contributions towards trying to explain this. So there's two other experiments we're going to talk about. So the first one is called Blackbody Radiation.
They use a black person for this?
No. The idea behind the black body part is that it's a perfect absorber or a perfect emitter, meaning that black will absorb every color, right? And so they called it black body radiation for that. And this was done by someone named Planck. And do I have a date for him? Because I don't really care about the dates so much. His name was Max. And he got a Nobel Prize for this, of course, eventually.
Blackbody
Radiation.
radiation.
And it's something that you guys are familiar with. If I heat an object, what happens? It gets hot and it radiates light, right? So like for instance, we can, you know, if we heat up, say, a piece of metal, at first it's just going to be a dull red color, right? And then as it gets hotter, it gets orange and then blue. Like what part of the flame is the hottest part in our Bunsen burners? Yeah, the blue inner cone, right? And eventually we might say something even gets white hot, right? And so depending upon the temperature, we get different colors. So if I make a plot of basically the intensity of light versus what we call wavelength. And for wavelength, we're just going to simply say different colors. We're not even going to worry about the mathematical terms for it. We're not going to worry about the Greek letters describing it. We're simply going to say that wavelength and kind of color are interchangeable to just kind of keep it nice, short, sweet, and simple. So what happens is, depending upon the temperature, you might get a curve that looks like this, or you might get a curve that looks like this, or you get a curve that looks like this. And so the peak shifts, and I didn't really show that very well. So like down here it's here, and then down here it's way over here. So notice the peak kind of shifts. And so depending upon the intensity of the light being given off, or basically the temperature we're at, so this would be low temperature, this would be high temperature, we should get a different colored light coming out. And if we take a look at our classical model, which is, light is a wave, what we get is that this predicts a line that looks like, I'm going to switch colors here, red. So the model goes like this. So here's my classical model. Now the classical model honestly sucks, meaning it fails at low wavelengths, or short, I guess is usually how we'd phrase it. Or sometimes this is also called the UV catastrophe. Because what it predicts is that eventually an object should emit UV light, and as the temperature increases, we should get shorter and shorter wavelengths of light. But we see that this is not what actually occurs.
So is the graph that you just did the classical model?
No, that's the actual experiment. So we'll go back to kind of color coding. This is the actual experiment. So the idea is that the actual experiment produces a very different result than what we would predict using Maxwell's equations and what we would predict from saying that light is simply a wave. And so what Planck said is that the energy of the wave, or since we're talking about light, we can say light, is quantized. And what that means is that it can only have specific values. And I'm going to go to a new slide and draw a picture. We're going to talk about what it means to be something that's continuous that can have any value versus something that's quantized.
What is that curve? The energy of the curve?
Oh, the blue curves?
No, I'm saying in the little black by the star, it says Planck's.
Oh, the energy of the wave or the light is quantized. So the classical model says that no matter what color light you can have any amount of that light, and so you can have any amount of energy. What Planck's model is going to say is no, you can't have any amount of energy. Depending upon what the wave is, or the wavelength of light, it can only have very specific energies allowed to it. And so it's saying that light is not continuous, that it's actually made up of much smaller little packets. Or you can think about it this way, it's kind of made up of little atoms or particles of light. And so we're kind of going back to that particle model, maybe, that Sir Isaac Newton kind of first said. So let's think about that. So we've got the classical model. And it says that light is a wave. And it would predict any energy, or allows any energy available, or any, let's do it this way. Any energy is available. Any amount of energy is possible. We have what's going to eventually be called the quantum model, or quantum mechanics. And it wasn't called that back then. This is the before it was kind of made. But this is going to say that light is quantized. Or at least what it's saying is that only specific values of energy are allowed. And the easiest way I can think about thinking about this is simply drawing a diagram. So this is just a wedge. And here's a ball on it. Or you can think about it as a ramp. And if I take a look at it, the height of the ball can have any value, right? What? Yes, this is under classical. That's why I drew it under the classical part. And so the idea is that the ball can have any height. What Planck's saying is that no, the ball can't have any height. It's more like the ball is on a staircase. And so here's my staircase. It's lovely. And so the ball can only have some values of light or height. So only some values of height are allowed. Or remember, we're really using this as an analogy for energy, and so classical says any amount of energy is available. Quantum mechanics says only specific values are allowed. And what this really does is this explains or predicts blackbody radiation perfectly. Well, maybe not perfectly, but close enough. And so it's really good. It explains this experiment. Now the key here is that, okay, so we got one model that says energy is quantized, and back then, frankly, Max Planck wasn't exactly world famous yet. And so a lot of people would have simply said, well, that's nice, it explains blackbody radiation, but that doesn't mean that energy has to be quantized, that energy or light waves might be particles instead of waves, because we have all this other evidence that really says light's a wave. And so this was the very beginning. He's the first person that postulated this, but it didn't get popular until sort of the next guy came up. What is what? Blackbody Radiation, BBR. Another one of Jay's abbreviations. What I really recommend is go through and read a little bit in the book. You'll find that the book doesn't have nearly the number of scientists I have. I think it mostly sticks with the whole line spectra and starts there. But it does mention all these other people. Hopefully we're giving enough additional information to help make it make a little bit more sense.
Can you just kind of run through why it explains black body and just summarize what it is?
The easiest way to say that is that because each wavelength of light can only have so much energy, that the curve goes down like this because each wavelength has too little energy. Honestly, I'm not really sure I can explain it without actually putting an equation on the board. And I really do want to avoid mathematics and equations.
I really want
And so what we're going to say is, and what I really want you to take from it is that classical wave model fails because it predicts this ugly red line. Quantum mechanics, energy is quantized, comes in only very specific values, explains it perfectly. That's really the only two key parts I want. And knowing that this is one of the first experiments that, kind of where quantum mechanics got its beginnings. It wasn't until the second person, though, to kind of start using this that we get some traction for it. And of course, this next person, so this is that second experiment, is Einstein. And what his experiment was, and he's famous for so much stuff, is the photoelectric effect. And this is one of the things that he actually got a Nobel. I think this is why he got the Nobel Prize eventually. I mean, they could have given him more than one, I'm pretty sure, if they wanted to. But I got to double check that. I should find it, which set of notes has all of my Nobel Prize stuff in there. But he did get a Nobel Prize at some point. And I'm pretty sure it was for this. It might have been for relativity. It might have been for this. I don't remember, honestly. It's one of those things where, like I said, he could have gotten more than one. And what the photoelectric effect basically says is that if I have a piece of metal, and I shine light on it, then what happens is electrons are ejected. And what they really used it for was to produce a flow of current. And this actually used to be how, do you guys remember when, well, you guys are too young. Oksana probably remembers. You remember when automatic doors, when you walked towards them, they took forever to open and you had to have the little cameras way out in front? Oh. Not in your country. Well, anyway, it used to be that they had all of the electric doors were run by this photoelectric effect, essentially. And then when you broke the light, the beam of particles or the electrons being ejected, then the doors would open. And so nowadays, I think they simply use cameras, so they can open them up well in advance of getting there. Yeah, they can also use that. So, I mean, we've made some progress on that. So the idea is that if we shine light, then those electrons are ejected. And it leads to a graph that looks like this. And I'm going to go on to a new page. I shouldn't have put this in the middle. So here's our frequency of light, or wavelength. And again, don't even worry about those words. Just think about this as different colors of light. And what happens is you get a graph that looks like this. No electrons. And all of a sudden there's lots of electrons. And this can be the number of electrons ejected. And we call this sort of graph something that has a threshold. Meaning, below a certain color, no electrons ejected. So this would be red light down here. And if I use blue light, Lots of electrons ejected. Now again, we've got the classical model, which simply says the color shouldn't matter. Meaning that what really matters would be simply how much light I shine on the object. But it turns out that no matter how much red light you shine on certain metals, no electrons are ejected. And the second you shine even a little bit of blue light on there, lots of electrons are ejected. So the classical model kind of fails spectacularly. Well, whatever, it fails. I can't even spell the word spectacular. And then a quantum model where energy is quantized works 100%. Meaning that in red light, there's just too little energy to eject an electron. Whereas in blue light, there's lots of energy to eject an electron. Another way to think about it is that sometimes energy is like a ping pong ball. Ping pong ball versus baseball. You can think about the photoelectric effect kind of in this analogy. If I have ping pong balls and I throw it at a window, what are the chances the window is going to break because I throw a ping pong ball at it? Slim to none, right? Now what if I throw 1,000,000 ping pong balls at it? It's still probably not going to break, is it? But one baseball pretty much breaks the window, right? So same thing with this. I can throw as much red light on this as I want, and there's just not enough energy to break the glass or to eject an electron. I take one baseball, I take one little beam of blue light, that's got enough energy to break the glass or to eject those electrons. And so the idea is that we really are beginning to believe that energy is quantized, and what that means is that light is kind of like a particle, in that we can have different energies just like we can have different sizes of particles. Okay, so how does this all tie together? Well, the person that summarizes this all together is called Niels Bohr. And what he does is he takes the observations about line spectra, he takes the observations about blackbody radiation and the photoelectric effect, and the fact that energy is quantized, and he summarizes them all together and says, then electrons are not in a cloud, but instead in orbits. Around the nucleus. This is what I would call the normal model of the atom. Like if you asked some Joe Blow on the street that had some amount of chemistry background what an atom looked like, he'd probably argue that it looks like this. Sometimes this is called the solar system model. And what it looks like is here's my nucleus with the positive charge, and then instead of a cloud, the electrons are in very specific orbitals. You know, so the third electron out would represent what planet?
I was kidding, okay? I need you to slow down real bad.
Okay.
Thank you.
So we can kind of think about this as Mercury,
Earth.
Venus, Earth. Okay, you guys are all going to have to take astronomy next semester, apparently. You didn't learn much, did you? So I think astronomy could potentially be good and bad. Depends.
Boring as shit.
You have to make life interesting for yourself.
I have
You
an app that shows it most stars. Like, you
Yeah,
can
that's
just
our
follow
map.
your like phone around.
Yep.
Show you. Yeah.
pretty cool apps.
I remember that being like the first cool app that smartphones did.
Yeah.
Do you remember that? Everybody's like, ooh.
I remember when you could do that on a computer monitor. That was pretty cool. You kind of had to, it couldn't really take a picture of the sky and tell you what you were looking at, but you could at least, you know, kind of look on the monitor and see where you were supposed to look. So the idea is that if an electron starts out here and absorbs energy, this means that it can emit one specific wavelength, one specific color. Ugh. Or if it goes between these two orbitals, then that's a different color. What? So this would be, each is a different color. So when electrons move from one orbital to another, they emit one specific color. Whereas Rutherford's model would say, since there are no orbitals and the electron can be anywhere, then it should be able to absorb and emit any color. The Bohr model says since electrons can only be in specific orbits, they can only, you know, emit or absorb specific amounts of energy.
I do have a question for you guys.
Yes, Jay.
What are you supposed to be?
Gandalf.
Gandalf the Grey.
I've never heard of it.
Are you shitting me, Jay?
Have you watched Lord of the
Lord of the
Rings?
Rings or
Yeah.
I can tell he's shitting me.
No, I'm not.
I've never seen the Lord of the Rings. Are you serious?
I've seen the Lord of the Rings, but how are you supposed to know? Like,
Who else wears a freaking pointy hat? Admittedly, it fell over.
Yeah, dumb stuff.
That's what I thought you were.
Future king.
No, Lord of the Rings is well before stinking Harry Potter and Dumbledore.
Yeah,
Lord of the
that's
Rings
what I
is like
thought you
4
were.
hours long.
Yeah, but I
How
guess
can
he
you
was
not fall
before
asleep in
Gandalf
the movies?
Berlin, so.
Okay.
You should be
She went
Colin
there, huh?
next year.
I should
Berlin was the original.
be who?
You have to have a couple hairs. Colin.
Yeah.
You only need to glue a couple hairs here.
So I got a question though, like, really?
Okay, Jay. Let's focus for another 20 minutes or so.
Oh, never mind. Go ahead, go ahead.
20 minutes.
It was about the concept.
Let's actually talk about Lord of the Rings.
Okay, so here's our Bohr model. It's a good model. It has two flaws, though. The first is that there's no reason it's quantized. It simply, it explains the results, but not why. And then the second flaw is it fails for elements with more than one electron. How many elements have one electron?
One.
Right, so it works for hydrogen. Wonderful. And it doesn't work for any other element. Now, here's the key. The mathematics behind the model, and especially when you start looking at 2 or 3 or 4 electrons, almost no model is very good until you get to really hardcore mathematics and quantum mechanics, meaning that it's just hard when you've got 2 or 3 or more interacting bodies with each other. And so it's not surprising that a simple model like the quantization failed for one electron. Are you okay, Aaron?
Wait, can you read number 2? Fails?
Fails for elements with greater than one electron.
I'm really not trying to pick on you, Jay.
I understand. What did you say?
Why are we in such a hurry?
I don't know if we're in a hurry.
Because we don't have class tomorrow, so we're jamming 2 and 1.
No, we're just going a little
Super speed.
Oh yeah, we don't have class tomorrow, do we?
No.
We don't have biology tomorrow either. Why do you think we're all little cute?
That's why everyone's like,
Yes, and they're all sleep deprived because they spent one night studying for chemistry and then the next night studying for Sarah's
No,
class.
because 2/3 of the campus was wasted last night. Is
and
exactly
we were
right.
studying.
Actually, nobody in this class. Huh? Really? I
Jewish.
guess.
I wouldn't say nobody in
this is on tape, just so you know. This could be held against you in a court of law or in Jeff DeVere's office. Okay, so the next person that we'll talk about is de Broglie. Don't worry, we'll talk for another 18 minutes. We'll stop at 2 o'clock, okay? Is de Broglie. And he's going to be famous because he can explain why the orbitals are quantized. And he's kind of famous for making one statement, and I'm going to paraphrase it, but basically what he said is that if light can sometimes behave like a wave or a particle, then why can't an electron behave like a particle or a wave? So raise your hand when you're done writing that down so I can keep track. Because we want to pause here for the, I don't know.
We keep writing, how do you know how many classes? Jay, you just talk as you write.
Because you
But
already
you
noticed
gotta
it.
think that after
I'm
you
waiting.
write-
I'm pausing. I notice most of you can't write and talk, so spend your time writing.
I'm sure I was gonna tell you, congratulations on being able to do that, but I can't do it.
Jess?
Or a particle.
Or a wave.
So where did you get your
No.
costume?
Wave or a particle.
Then why can't?
Okay.
So notice that it's opposite, right? Light, we're saying, is normally thought of as a wave, or it can be a little particle. Electrons were normally thought of particles. Now we're saying, well, couldn't an electron look like a wave? Which is pretty radical if you think about it, because the idea being that in classical mechanics, things were either a wave or a particle. And under quantum mechanics, what they're starting to say is that things are a wave and a particle, meaning they can be both. That's like saying we've got boys and we've got girls, and then it's like, no, really, you can be both. Which arguably you can be, but it's not very good. Or maybe another less weird example would be, it's like saying you're pregnant or you're not pregnant. Well, quantum mechanics is saying you can be both, which doesn't make any sense,
You
right?
can be kind of pregnant.
Yeah, you can be kind of pregnant.
Wow.
Or
You can be in the process of miscarrying.
let's not take the analogy to any weird extremes, okay?
How can you kind of be pregnant? Can you just hear me?
But that's
That's the analogy you can't.
That's the point of quantum mechanics, is it does get weird. It does actually say things like you can be more than one thing at once. And it's not until someone observes it that you can determine which way it is. And so quantum mechanics gets really weird. And so de Broglie is taking a pretty bold step forward here, saying that something that we normally think of as a particle, because if you think about it, Thomson measured an electron's mass, he said it had a shadow, and he said basically it's a particle, and everyone thought that. And all the experiments up till now really do say that electrons are particles. And he's saying, well, wait a second. We thought light was a wave, and now we've got some experiments, Blackbody radiation and things like that, and the Photoelectric Effect that says, no, it's quantized and it's a kind of particle-like. Well, he's saying, well, okay, let's do the exact same thing. Let's take something that we think is a particle and treat it like a wave. And so what happens is that if I take a look at an orbit like this, and I draw a wave around it, if the wave matches up perfectly, it's allowed. So I'm bending a wave in an orbit. And what he's saying is that, yes. So here's my orbit. Here's my wave. And what happens is if the wave doesn't match up perfectly, if it's out of phase like this, then it's not allowed. Or since, well, it's not allowed as an orbit. So, well, this technically is what we call constructive interference and destructive. Now I'm going to use an analogy because this is too weird to try to imagine, okay? In that, if we really think about it, you know, we're not used to thinking about things as waves, and we're not used to thinking about waves kind of going in a circle like that either. Another or better analogy might simply be that if we have a piano chord, you get how many tones out of it? You're allowed one tone, right? Now you can modulate it and you can vary it, right? And it's got different frequencies, meaning you can double it or you can halve it. But what it's really saying is that different lengths of piano wire would produce different tones. Well, same thing here, and with light waves, some tones are allowed and some are not. And that if the light basically fits some criteria, and again, I don't want to do any math here, but the idea is that if light fits specific criteria, then it's only allowed to be certain orbits or distances from the nucleus. And so this is where quantum mechanics gets weird, because it says that things can be more than one thing at a time. Or that our simplistic view of the macroscopic world, where we think of things like baseballs as particles and we think about an ocean wave as a wave, is great on a macroscopic scale. You can't have both. But quantum mechanically, we're actually saying that you really can have both. And in fact, one of the interesting things is that a baseball technically has a wavelength associated with it, meaning you can treat it like a wave. The problem is that the wave is so much smaller than a diameter of an atom that it's not like you see the baseball oscillating in space or anything like that. It's not like you see it behaving like a wave because the wavelength is so small we can't observe it. And so one of the things that quantum mechanics does great is it explains things on the size scale of an atom or an electron very well, and then degrades naturally into what we think about as our macroscopic view of the world. Whereas if we do our macroscopic view of the world and try to apply that to something as small as an electron or an atom, it fails spectacularly. And so one of the things that we can say about classical is, you know, it gets the macro right, and it fails for, you know, like atoms and waves, or arguably those are smaller than the microscopic, but, you know, it fails for microscopic. We can say that quantum mechanics gets the microscopic, or the atoms and the wave part right. I guess we should say atoms and electrons right. And it kind of degrades to the classical view for large objects. So the idea is that we can adopt quantum mechanics as an explanation for atoms and electrons without changing our view of things like gravity or how things work on a macroscopic scale. It doesn't affect that because all the wavelengths that we would normally expect are too small to even measure or see. And we can't do the opposite for classical. We can't go from large to small with classical at all. It fails.
So Newton and Hubble were right.
Exactly. Wow. Out of the mouth of Cody.
You don't even spell my name right.
Newton and Huygens are right. Wow, that's kind of bizarre, isn't it? I mean, seriously, that's one of the screwed up things about quantum mechanics, is that it doesn't fit any concept or model that we have as normal people. Meaning, one of the reasons is very tough to grasp, and one of the reasons why we shouldn't even have given this lecture, but I usually like to give it. It hopefully gives you a little bit of an idea of how weird things are and how things on a scale of atoms really don't behave like we think they do. Some of it will be. I'll make it very obvious what's on the test. because you'll notice that it's very obvious in the homework. Huygens. So they're both right in their own ways, kind of. And, you know, obviously in the 16th century, they didn't even know what protons, neutrons, and electrons were or anything like that. And so obviously you need to modify their base theories to account for that, but it's okay. This is also sometimes called the wave-particle duality. This whole concept of things being waves and particles versus the classical model of waves or particles. Meaning that we really have to think about things as being both and not being either or. So both, it can be both, not an either or. So it really is possible to be pregnant and not pregnant at the same time. It's really possible to be dead and alive at the same time. You know, there's some weird stuff that goes on with quantum mechanics. One of the things that I find most interesting is if you go back and you kind of read some of the debates that Einstein had with other people, and there's this whole series of letters that go back and forth between all the people that are trying to figure out quantum mechanics. For instance, Einstein never actually believed in quantum mechanics. He said it's a, well, I doubt he swore, but it's a screwed up theory that explains everything wonderfully, but can't possibly be right because it also predicts so many other screwy things. The bad part is that most of the screwy things it predicts we're actually seeing come true, or, you know, we can't disprove. And so Einstein always said that essentially there's got to be a better theory than quantum mechanics, and we just have to wait around and find it, or have to think really hard and come up with it. He never actually really truly liked quantum mechanics. And this is like, you know, probably one of the most brilliant people who have ever existed. And he still was like, gosh, it's too screwy even for me a little bit. And there was a whole series of debates that goes on between him, Niels Bohr, a guy named Schrodinger, Maxwell Planck, and a bunch of other people that both support and don't support the whole idea of it. For instance, a lot of science fiction topics, like you've heard of parallel universes, right? And, you know, all sorts of different things like that, that all comes from the ideas behind quantum mechanics, that really in another universe there's one little tiny thing different. Maybe Britney's hair is blonde in that universe or something. You know, it's probably a crappy universe if your hair was blonde, admittedly, but, you know, that possibility might exist. Are you putting me on tape? Well, at least let me put on the beard then and get the staff.
You should put on the beard. I just want people on Facebook land to know how ridiculous my character is. That's not, isn't that supposed to say? There you go.
Oh, good grief. You know, Taylor, just because you did well on...
Not yet. Hold on. I can't hear if I'm okay. Wait. I don't. They said wait, not wait.
So did anybody?
Okay. 2 last scientists and then I'll quit, okay?
Will, you'll quit?
Yes.
Because I'm about to quit.
I ran out of paper.
Heisenberg! Yay!
Yes, Heisenberg. So if you watch Breaking Bad, he picks the name Heisenberg somewhat based on the actual fact that there was a person named Heisenberg that was a scientist. Now, turns out Heisenberg was actually kind of a really nice guy, and so I don't know why he picked him. I don't think...
Is he a chemist?
Yeah.
Okay, that's
Well,
why
chemist
I'm
slash physicist.
Breaking Bad too.
What?
He's a nice guy in Breaking Bad too.
I don't know. I've only watched about the first 4 episodes where they dissolve a guy, okay? Anyway, one of the things that Heisenberg is famous for is his uncertainty principle, which simply says that you can't know the position and momentum. Now, momentum's a physics-y term. We're just going to simply say the direction of an electron at the same time. Now, he also says that you can't know it for any object at the same time. So, for instance, what he's really saying is that if I have a baseball, I can't both throw it and know exactly where it is and exactly how fast it's going or what direction it's going in. That you can't know both pieces of information at once. And you guys would say that's false, right? You can get a little pitching gun and you can measure how fast the baseball is going, right? And you can see which direction it's going. Well, again, this is quantum mechanics, meaning that on a classical model, it really is true. You can't know exactly where the baseball is. But the error in where the baseball is so tiny, we can't tell it. But for an electron, the error in the location of an electron's position, if we know exactly how fast it's going, is bigger than the size of the atom. And so what his uncertainty principles really is saying is that we can't know two pieces of information about the electron at the same time. And so it's impossible for electrons to be in orbitals, because if it was in orbitals, then we wouldn't know how fast it's going. And that if we knew how fast it's going, then it can't possibly be in orbitals. And so he's really saying you just can't know really where the electron is. So we really don't know where the electron is. Or basically the uncertainty in its position is bigger than the atom. And what that really means is that orbitals are meaningless. Well, wait a second. So basically he's saying that Bohr and de Broglie's models don't work. Bigger than the atom. So the uncertainty in the position of the electron is larger than the actual atom itself. And so he's basically saying that Bohr and de Broglie models don't work. Now, the problem is he doesn't have any better model. He just simply says they can't work. And it's like Cody saying, that doesn't work. I don't have a better solution, but that doesn't work for me. Fair enough. In fact, I find a lot of people in the world are more than happy to point out all the flaws in it, but can never figure out how to fix it.
I don't like that either. People who don't want don't have a solution.
Don't work. I don't know which part you're on. Orbitals are meaningless. So what he's really saying is that here's the Bohr model. It says the electron is here. He's saying that the uncertainty in the position of the electron is it could be anywhere in a cloud. So he's actually kind of advocating a little bit the Rutherford model. Now, don't worry about it. The only reason I really bring him up is because, first off, everyone recognizes Heisenberg's name. And if you do any amount of science, eventually you come up with that idea of a Heisenberg uncertainty principle, where you can't know absolute information about anything. There's always some error in every measurement involved. And for instance, like I said, the error in measuring the position of the electron is bigger than the entire size of the atom, so we really can't say where it is. And because he leads to the last scientist, and this is where we'll end up, his name is Schrödinger. Schrödinger.
Schrodinger's cat.
Yes, and the reason we talk about him is he's famous for his cat.
I have a really cool shirt.
Yeah, how many people have heard of Schrödinger's cat?
What?
Only the cool people. We'll talk about it in a second. So what Schrödinger came up with is he came up with a mathematical model which is sort of hard to visualize. Although we're going to work on that on Monday, visualize. We're going to save that for Monday. And it's basically also a statistical model. Statistical, or based on probabilities. And that allowed it to circumvent Heisenberg's flaws. Or maybe we would say Heisenberg's criticism of orbitals. And so what he says is that basically the electron has a probability of being in certain spots. But can be elsewhere. And I got to be honest, if you guys kind of lose it at this point, that's okay. Frankly, if you lost it earlier, that's okay. Because once quantum mechanics, once you start really trying to think of things on the scale of atoms and electrons, our macroscopic view of how the world functions doesn't work anymore. You can't just say, oh, an electron is just like Earth orbiting the nucleus or the sun. It just doesn't work. It's not like that. And what it really comes down to is you almost have to be really, really, really good at math. How many people here are really good at math? You've all had calculus?
Yep. 3 times. Failed it all.
I took it for a semester.
Okay, really good at math would be like calculus, differential equations, matrices. Meaning, I got to be honest, I'm not even going to claim to be good at math, okay, under that definition. Meaning, to really understand these models, you have to be really good at math and understand the interaction between the various parts of the equations. Way, way beyond us, okay? What we really want to take from it is simply the results of all of those complicated equations. And so we'll end on talking about Schrodinger's cat. So here's the experiment that was proposed to say why quantum mechanics was silly. So he took a cat and put it in a box. And then he put a cyanide capsule in it. A cyanide capsule in the box. Cyanide, when you break the capsule, it produces cyanide gas, very poisonous, kills you instantly. So he's not very nice to the cat, okay? He put the cat in the box, he put the capsule in the box, and he put one radioactive atom. And the idea is that when the radioactive atom decayed, the cyanide capsule breaks and kills the cat. So he closes the box. And then because there's a probability at any given time that radioactive nuclei has decayed, then what he basically says is that once I close the box, is the cat alive or dead? You can't possibly know if the cat's alive or dead until what? You open the box, right? And then you can observe whether the cat's alive or dead. So what he's saying is that's kind of like quantum mechanics. Before you open the box, before you look at an atom and where the electrons are and everything like that, the electrons can almost be anywhere, basically. We can't know that. It's only after we open the box or make an observation that we can tell whether the cat's alive or dead. And so technically when the box is closed, the cat's both alive and dead. And if you don't really understand that, or that sounds silly to you, or the idea of being pregnant and not pregnant, or alive and dead at the same time, that's why quantum mechanics is weird, okay? It really says that until we make an observation of a system, we really cannot know any information about the system. And the very act of observing the system also affects the system.
There's a lot of really cool YouTube videos on it, too.
Yes, go watch some YouTube videos, or watch the entire series of No, just kidding. No, don't watch Star Trek. That'll confuse you more than anything else, probably, since most of the stuff they make up is silly. But the idea is that quantum mechanics is weird, that we're actually going to get to a point where mathematically trying to understand this theory is usually a grad school course, meaning I took an entire semester just on this. And I don't remember crap about it, I'll admit that. If you gave me a test on it, I'd fail, and they'd probably take away my PhD and say, screw you, you obviously didn't remember anything. So realize this is difficult stuff. What we're going to come back in on Monday, though, is we're going to come back in and say, okay, we don't need to know all the nitty-gritty math. What we need to do is understand the result of the nitty-gritty math. And we also have to just come back on Monday and say, okay, we had a 3-day weekend, and we're all rested, refreshed, and ready to go. We also might want to say things like, you know, congratulations on the test. Everyone did very well. I was pleasantly surprised at